Hey guys, welcome to the lesson on triangle sides and angles. We're going to start with our quick do now. We have two questions. What is an isosceles triangle? So you can either define it by the definitions we went over earlier, or you can actually draw me a picture. Here's my triangle. And an isosceles triangle, a requirement for isosceles triangles is that they have two sides that are congruent. So you can just show me that, and we would be good. To state for part B, state or draw the alternate interior angle theorem. So again, you can either state it from the definition that we reviewed or we went over in lesson 4, or you can also show me by a picture. So I'm going to go ahead and draw a picture of it. So we can have any two parallel angles. Those are my parallel angles cut by a transversal. Here's my transversal. So if I want to show alternate interior angles, I can state that this angle and this angle are congruent. You can also see these alternate interior angles, assuming these are parallel. You can also see them more classically as this. So alternate interior, this one, and this one will be congruent. So we have triangle sides and angles. Our objective is given an understanding of triangle angles. Students will use transversal properties to prove the interior sum theorem and exterior angle theorems. So students will use our first blank here. Students will use transversal properties to prove the interior sum theorem and exterior angle theorem. So that's exactly what we are doing in our class. Here is our very first proof. So we're going to use transversal theorems for the following proof. Given a straight line, so here we have a straight line, we know that it's 180 degrees. Prove that the sum of the interior angles of any triangle, this triangle, would be 180. Again, the sum of interior means if I add up C and I add up A, B, and C, I should get 180 degrees. So this is the given information. Given that angle XCA, that would be this angle here, plus this angle here, which would be, or plus YCB, this would be this angle out here, and plus ACB, this angle right here. If I add all three of those angles, I should get 180 degrees because it is a straight line. Or a better representation of the given information is I just want to add up this entire angle. That's what we care about. So let's start with the given information. We know that, we know that that's going to add up to 80. So let's start out with number 2. It says XCA. So we're looking at this angle here. XCA is going to be congruent to measure of angle A. Well, if I extend this out, actually, let me grab a different color to make my point. If I were to extend this line out, and I extended this out, I have two parallel lines, L, and we'll call this M, and it's being cut by this transversal. Or if I were to extend this one out, this would be my transversal. So if I have this transversal, then I can say, hey, this is congruent by alternate interior angles. So we can state that the reason is alternate interior angles. We're going to look at step 3. So in step 3, we can also state, well, if these two lines are parallel, L and M, then the segment CB is also a transversal, or it's also cutting my two parallel lines, making it transversal. So I can state that this angle has to be congruent to this angle. Well, again, I like to visualize what I'm going to write first. So I drew it first, and then I'm going to write it down as a statement. So I have that angle YCB is congruent, YCB, to measure angle B. And if we look at our picture, that's by alternate interior angles. So now the only angle we have left, or that we haven't touched, is angle ACB. Well, if we look up here, angle ACB is this little corner here. That is literally just equal to my measure angle C. It's the same angle. So ACB is the same angle, it's just angle C. It's just given it by a different name. So we can actually write angle ACB is congruent to my measure angle C. And this is because it's the same angle. So now we have all these statements written out. If we just add them together, or we're going to use this first statement up here. If I substitute XCA for my first statement, I'm going to rewrite this down. If I substitute XCA, we see that XCA is equal to M measure angle A. So I can write, hey, measure angle A. If I substitute YCB, that's the same as measure angle B. And if I substitute ACB, that's ACB, that's the same as measure angle C. And we said from our first statement, or from our given, that's equal to 180 degrees. So this is just by substitution. And we're done. So we showed that if we add up all of my angles inside, we have A plus B plus C, it should give me 180 degrees. Well, this became such a big notion that it actually got its own theorem. It's called the triangle sum theorem. So it's the sum of the measures of interior angles of a triangle, any kind of triangle, is 180 degrees. So if I were to just kind of play around with this picture, that means this angle A plus this angle B plus this angle C is going to equal 180 degrees. Let's see an actual example of this. Here we have our triangle, and we have three angles. So we're going to go ahead and add up my red angles. If we add them up, we get 33 plus 47 is equal to 80. So better yet, I'm going to write an expression. So we have 33 plus 47 plus my sad x is equal to 180 degrees. If I add these two together, I have 80. I bring down my x is equal to 180. I subtract 80 to both sides because I'm solving for x. When I do this, this goes away. I bring down my x. And when I subtract, I get 100. So x would just be equal to 100. If we were to substitute that back in, we get 100 plus 33 is 133 plus 47 is 180. It checks out. Here we have another proof. So it says this time, given that the sum of a triangle's interior angles is 180 degrees. So we just proved that the sum of all of these angles is 180 degrees. We need to prove that measure of angle D, this one up here, out here, is congruent to the sum, or to measure of angle A plus B, the sum of A and B. So my given information is my interior sum theorem, angle A plus B plus C is equal to 180. And we have to show that this outside angle of this exterior angle is equal to A and B, or the sum of A and B. Our first statement we have up here. Number one will always be given. It's always given information. So we just rewrite what is given to us. The second part, supplementary angles. This will be measure of angle C plus measure of angle D is equal to 180 degrees because they are supplementary. They create a straight line. You could have also used linear pairs. Therefore, if we rewrite this statement, so better yet, let me make a little bit more sense out of this. Let me write measure of angle D plus measure of angle C. Because by doing so, let's rewrite this a little side work. Measure of angle A plus measure of angle B plus measure of angle C is equal to 180 degrees. That was our given statement. Our second statement was that measure of angle D plus measure of angle C is equal to 180 degrees. You can see the similarities. It ends the same, and the red, so the blue is the same, which means the red, if both of these are equal to 180, the red has to be the same. So if these terms have to be the same in mathematics, we call that equality, which means that measure of angle measure of angle D has to be equal to measure of angle A plus measure of angle B. That has to be the case. So that's what we sum up here, is that measure of angle D is equal to measure of angle A plus measure of angle B, and that's what we needed to prove, and that can also be done by the transitive property. That's what we needed to show. So we literally stated that this angle D is the sum of A and D. So again, this can be written formally as the measure of an exterior angle of a triangle is equal to the sum of the measures of the two non-adjacent interior angles. So there's a lot of big words there just to say that, hey, this measure angle 1 is equal to measure of angle A plus measure of angle B. Done. So let's take a look at an actual example of this. Here we have a little bit more complicated triangle. So we're saying that this angle here is equal to angle L plus angle J. So if my exterior angle is equal to L and J, we just have to write this down. We say, hey, that's 2x minus 5 should equal the sum of those opposite adjacent, non-adjacent angles. So we have 70 degrees plus x amount of degrees. We just solve for x. We go plus 5 plus 5. This goes away. We end up with 2x is equal to 75 degrees plus x. We're going to subtract an x to both sides. Subtract an x to both sides. What you do to one side, you always do to the other side. We're just left with x is equal to 75 degrees. Now this is what x is equal to, but our problem is telling us to find the measure of angle JKM. So we have that the measure, or better yet, the measure angle of JKM is equal to 2x minus 5. Well, we know what x is equal to, so we're just going to substitute that in and then continue to solve. So that's equal to 75 minus 5. So if we keep going, measure of angle DKM is equal to, well, 2 times 75 is 150 minus 5, and our last reduction, 145. And we're done. So that's what our angle is equal to. For our next proof, we have that given triangle ABC is an isosceles triangle, we have to show that angle A is congruent to angle B. All right. So what we have up here so far, I'm going to write the given information, is that AC and BC are congruent. This is by the given information. If it's an isosceles triangle, both sides, if we remember our do now, have to be congruent. So that's given. The second is by perpendicular bisector theorem. Since these two are congruent, this ray will bisect AB perpendicularly. So this perpendicular bisector, which means that this, it's actually the converse of perpendicular bisector, which means that this has to be congruent to this. So if we want to state our part of our next statement, we state that AM has to be congruent to BM. and that's by the perpendicular bisector theorem. Moreover, CM is congruent to MC. This is one of our favorites. It's the reflexive property. So let me double this congruency mark and triple this congruency mark. So now we created two triangles. We have triangle ACM and triangle BCM. Well, since all of these sides are congruent, we can state that triangle ACM is congruent to triangle BCM. This is by side-side-side theorem of congruency, triangle congruencies. So if that's the case, then we know that corresponding parts of corresponding triangles are congruent. So anything this triangle has, this other triangle has to have. That's what it means to be congruent. So let's go ahead and write our final congruency down. We have angle A. This angle has to be congruent to angle B. And I'm going to write by triangle congruency. Or you can also write corresponding parts of corresponding triangles are congruent. Either one is good. So this would be more by definition. So this actually, what we just proved here is that whenever we have an isosceles triangle, the opposite angles have to be congruent. So if two sides are congruent, so are the base angles. The base angles have to be congruent. Well, we come up with two theorems. We have the base angle theorem for isosceles triangles, means if two sides of a triangle are congruent, then the angles opposite to them have to be congruent. So in this case, if these two sides are congruent, so are these two angles. And we have its converse. We work the other way around. So if our angles are congruent, then opposite sides must be congruent. Those are just properties of isosceles triangles. Finally, we have our exit slip that we will be working together. So again, guys, just remember you can pause and move through this video as you need. Work out the examples on your own and then kind of just check your work. So again, I hope this helps. See you guys next time.